Hello everyone. Welcome to a short discussion of general 2 and 3-dimensional motion. Really this is just kind of combining two previous ideas together. The idea of a general motion where we use derivatives, right, as opposed to kinematic equations, which is only for uniformly accelerated, right, and unit vector notation, which allows us to write in 3 dimensions all at once. So consider an object moving in 3 dimensions. To help you with this, right, think of this maybe as like, say, the bottom corner of a room. Right, so this is a bottom corner of the room. The room's out here. So say we have an object that moves like this. Watch it again. Can you kind of see that in 3 dimensions, right? It's just kind of moving out there somewhere in the room. Well, how could we describe that motion? Well, before we do the entire motion, let's just talk about a particular point. Let's pick a point along that motion. Right? How could we describe the position of that point? Well, one thing we could do here is to draw a vector from our origin to this point. You'll notice I'm denoting this with a lowercase r. This is a new symbol for us that we haven't used before. It's traditionally used for 2 or 3-dimensional positions. So this is called a position vector, okay, denoted by an r. This is opposed to our 1-dimensional x, y's, or z's, right, that we've used in the past. Right? This is a position vector, so in multiple dimensions, if we're going to write it, we usually write it as an r. Well, how could we then describe this position vector? Unit vector notation. We draw a little box around it, a little rectangle. Note we can now describe this vector, right, using the 3 perpendicular components. The one parallel to the x-axis, we might call x. The one parallel to the z-axis, we would call z. Notice, perpendicular to the other one, right? These are perpendicular components. Helps if you kind of draw them parallel, right? Draw the little right angle things parallel to the actual axes. Helps in your diagramming. Note, these are head to tail because you're adding them together. And then the y component, or vertical component, which is perpendicular to both x and z, right, is y. Add x to z to y, and you get r. But you got to add them vectorially. How do we add them vectorially? Well, unit vector notation, of course. Right, where I cap, j cap, and k cap are the unit vectors. Those, again, are vectors of magnitude 1, right, that are for indicating direction only. Right? X is horizontal, j cap is vertical, and k cap is in and out, right, in a typical right-handed coordinate system like we have here. Right? So these are vector components, right? And x, y, and z are scalar components. Right? They're just the magnitudes. So remember here, the unit vector, the I cap, the j cap, the k cap, indicate direction. So this is a 3-dimensional position vector. Really nothing new, right? We kind of described that before. But when we did it, we really just used it to describe that, okay? What are we going to do here, or we used only 1 dimension at a time, say? So what happens in a 3-dimensional motion? Well, as you might imagine here, the position might change, right? Change in position. This is technically displacement, right, in 3 dimensions, delta r, as opposed to delta x, delta y, delta z, which are 1-dimensional displacements. Right? Then your x, y, and z might actually be functions of time. All 3 of them, or any one of them, or at least one of them's got to be a function, some function of time for an object to be moving, right? So that it's changing as time goes on. Right? So that would be a displacement, if you will. Okay? That's really the theory behind what we're doing here. I'm just going to do one little example for you. This is not something that they really ask you to do all that often, if ever, on an AP test, but it's kind of nice to see it, and again, it kind of puts together our unit vector notation and, again, some of our differential calculus. So here's an example. Let's say we are given a position, right, of an object in 2 dimensions here. I'm going to do a 2-dimensional example because it's just going to be easier for me to draw out at the end, okay? So the position is given by 2t I cap plus negative 4.9 t squared plus 3 j cap, where the units work out so that the position is in meters. All right, so for example, for this to work out for 2t to be meters, since t would be in seconds, the 2 would have to be in meters per second. Right, so that would work out to be meters. So you can kind of follow that around. This would have to be in meters per second squared. This would just be in meters, right, so that everything works in meters. This is one of like 3 different ways that they sometimes show units again. There's this way, there's actually writing a unit on each one of the coefficients, and then there's maybe listing out the units, where they might say where the units are in meters per second squared in meters. So I want to know what the velocity and the acceleration functions are. Okay, notice I didn't say at a particular time, which really isn't much harder because you just have to evaluate it at a time, but right, I just want the full functions. This is where differential calculus comes in. Right? The power of the calculus is to be able to find the entire function at the time, not just the slope of the tangent line, right? Which is what we're finding for the velocity. So as we've defined in the past, the velocity function is simply the derivative of the position with respect to time. And notice here I'm using an r because we have a multi-dimensional position function. It's not just an x or a y or a z. So if we plug in what r is, and then we have to follow our derivative rules. First off, this is a sum, right? And the derivative of a sum is the sum of the derivatives. If you're really good, if you've had a semester of calc already or so, right, you can skip these steps, right? It would be really nice to see at least this first step, if not these first 2 steps, when you're doing a free response problem so that the AP can know what it is you're trying to do. Right? Some of you have been caught on that a bit on some of the tests where you haven't written out steps, and I can't give partial credit without those. Right? You don't have to show all of the calculus work or algebra work in between, but you got to show kind of where you're starting, right, before you get to where you're ending. All right, anyway, we take each derivative one at a time. Derivatives, you multiply by the exponent, subtract 1 from the exponent, right? That is the power rule. So this is an exponent of 1, so 2 times 1 is 2. T to the 1 minus 1, well, that's t to the 0, and t to the 0, just as anything to the 0 power is 1. So 2 times 1 is 2. Over here, we get negative 4.9 times 2, which is negative 9.8. T to the 2 minus 1 is t. And the derivative of a constant is, of course, 0, because every derivative is a rate of change, right? It's a slope, remember. And derivatives of constants, slopes of constants, are 0. So, hopefully this wasn't too big of a reach at this point. Again, if you're in first semester calc, you'll get much better at this, right? I promise you by the end of the year, right, this is going to seem pretty easy, right? If it's a little challenging for you now. Write out all the steps that you need. You might have to go back and look at your power rule and things like that. Do remember that on an actual AP test, the power rule is actually on your equation sheet. Right? So it's not something you have to memorize if you've forgotten what it is. It's one of the things that's on the equation sheet. So this is the velocity function. And of course, if I asked for it at a particular time, we would just need to evaluate, right? We just have to plug in for the time. But I want you to notice something here about this velocity function. Note that there is no t, no time, in the x component of this, the I cap part. Well, what does that mean? What kind of a velocity, what kind of a velocity does this object have horizontally? Just the horizontal part. Well, since there's no t, that makes it constant. On the other hand, the vertical component of the velocity, that's this, right, is constantly changing because it's a function of t. Not t squared, not square root of t, not 1 over t, not some funky big long polynomial, right, function of t here, but it's just a t, right, which would make a linear graph and therefore has a constant slope, right, so it's constantly changing. This is actually a motion we know, but just to make sure, if you're not seeing it already, let's do the second part, and I'm sure for most of you it should pop out at that point. If we want to find the acceleration, Well, of course, the acceleration is the rate of change of the velocity, or the derivative of the velocity with respect to time. Or if you want to be fancy, it's the second derivative of the position function. We plug in our velocity function. The derivative of the sum is the sum of the derivatives. This is the derivative of a constant with respect to time, so it's 0. Here we multiply by 1, subtract 1 off the exponent. T to the 0 is 1. So we get an acceleration function of negative 9.8 j cap. Notice the acceleration is completely vertical, and since there is no t, that acceleration is uniform. And it is our old friend, negative 9.8 meters per second squared. So what kind of motion has a constant horizontal velocity and a uniformly accelerating vertical velocity with an acceleration of negative 9.8 meters per second squared here on the Earth? Of course, this is projectile motion. So this is actually projectile motion written out in unit vector notation. Traditionally, we've written it as two separate equations, right? One for the horizontal part of the motion and 4 that we can really write out for the vertical part of the motion because it's uniformly accelerated, and therefore we can use the kinematic equations. Most commonly, we use the third kinematic, which is really what this one looks like, right? That's the 1/2 gt squared, right? Plus the initial position. And so this is, the third kinematic here, and this is really just our constant velocity equation, right? Now, here's one thing I've seen them do on a few tests, and we've actually done this, I believe, once or twice already, but just to kind of work it through again. What if instead of writing the position as a function of time, which is what we have up here, what if I wanted to know the position as a function of the position? Maybe the vertical position as a function of the horizontal position. Y is a function of x, right? Function notation. And then I want to make a graph of y versus x. Okay, so in other words, I don't want a time in this equation. Well, here's one way we can do that, right? First off, we can split this single equation into two equations. This is really the horizontal position equation, right? The horizontal position as a function of time is just 2t. You okay with that? And the vertical position as a function of time is negative 4.9t squared plus 3. This is the more common way we've written it in the past, right? Instead of putting it in unit vector notation. Well, what's the same for a projectile, whether you're looking at the horizontal part or the vertical part of its motion? Yeah, the time is, right? That's why we don't put a subscript, right? There's no tx and ty, right? We just put t. It's in the air the same amount of time regardless of which dimension you're looking at. So, if we want to eliminate time, yeah, simplest way, solve this one for the time, substitute, and then it's just a matter of simplifying. This one's fairly straightforward, right? Square this if you want to write it out, right? I know I've added some sig figs, don't really worry about it. That's just to make my graph nice. So this then would be the vertical position of the object with respect to the horizontal position. And don't lose that squared, that's very important. Note, no time in this, right? So you could use this equation to say, okay, at any horizontal position, where is the thing vertically? And vice versa if you do some algebra. So what would this look like if you graphed it? Well, first of all, let's remember this is projectile motion. So, and notice here, the squared. So hopefully you're saying it should look something like this, which is in fact what it does look like. Put this into a program that we use sometimes, a Pascal program, and graph the function. Right? And this is what it looks like. Notice, though, that it's only the back half of the parabola. This is vertical position as a function of horizontal position, not of time. Notice here that it's only half the parabola. Well, why is that? Well, if we go back here to our velocity functions, notice at 0 time, right, what's the vertical velocity? Vertical velocity is 0. right? So it doesn't have an initial vertical velocity. Note, you can see that in the equations, right? Because look at this equation, right? If this is the third kinematic, this is the 1/2 gt squared, this is the y sub o, but you don't see a VOYT component to this third kinematic, right? Because VOY is 0, right? And that's why it's only half the parabola. If you have a VOY which is not 0, that means you're shooting it at an angle, right? And you'd get at least some part of a parabola, extra part of a parabola, depending on the heights it's starting at, right? Are they the same? You'd get the full parabola. Is it starting at one height and ending at a different height? You'd get, still a partial parabola, but more than half. So this is our equation that we've seen many times, our graph that we've seen many times of projectile motion with 0 initial vertical velocity. So again, note how we just did this little trick to eliminate the time. It's really solving a system of 2 equations by substitution. 2 equations with 2 unknowns, by substitution in Algebra 2 language. But we chose to eliminate the time out of here in order to get y as a function of x. I've seen them ask this a few times on a free response problem. So I hope you enjoyed this little discussion of general 2- and 3-dimensional motion.